Yeah, next speaker is Shigeo Kida from Kyoto. Talk on the statistics of passive vectors in an unstable periodic flow of the Couette system.
This is an attempt of application of unstable periodic flow in Couette system for statistics of passive vectors. Got it? Okay. And so we consider this system the flow between two parallel plates which move along themselves. And so we consider the very small box, the flow in small box called minimal box, and size is this. And we use the spectral method in simulation with this number of mode, axial, wall normal, and span-wide direction, and with Fourier, Chebyshev Fourier expansion. And the total number of independent variable is 15,422, and Reynolds number 400. And so today we use the unstable periodic flow, slightly different from this, but the same branch. And first I show the turbulence state simulation. This box is actually a computation box, and upper plate move into the screen, and lower surface come to us, and we have low speed streaks in the middle and two streamwise vortices in the two sides. And in this simulation, the turbulence simulation, we see the nice repetition of appearance and disappearance of the low speed streak and span-wide vortices. And of course, this is turbulence, so this is not periodic and not repeat itself. And this is the unstable periodic flow with same Reynolds number. I forgot to explain this. Gray one is the ice surface of constant velocity, and red and blue is the represent vortex. And this behaves very similarly with the turbulence simulation. But this case is exactly periodic, so it repeats forever. So this is a comparison of the low order statistics between the two fields, and they give this almost same statistics for low order values. This is mean velocity. This is RMS velocities. And this is the snapshot at 10 time phase, single period. And this capital T, the periodicity, time period. And so this flow, time goes on like this, and it comes back to the first one. And now I compare some characteristics in two flows. The motion in turbulence is chaotic, and it is periodic in time in unstable periodic flow. And here the flow is unpredictable, but in unstable periodic flow it's repeatable. but they give the same, nearly same low order statistics. Because in unstable periodic flow it's periodic, so we can take the sample as many as we like if we continue the simulation. So we can increase the accuracy of statistics here, but not in TEB. This is one merit, one advantage to use the unstable periodic flow. The subject we consider here the some property of turbulence mixing by examining statistics of the passive vectors in unstable periodic flow. And particular, we focus our attention to the relation between the coherent statistics, structure, like streamlined vortices and low speed streaks, ejection region and sweep regions, and the mixing property. This is the subject. And first, I just mention about the orientation of passive vectors. In laminar flow, two passive vectors which start at same position but different orientation will align as time goes on, but the alignment is very slow. On the other hand, in turbulent flow, they align quickly, typically exponentially. And this difference may be understood by difference in the value of Lyapunov exponents in these flows. Now we examine the alignment property numerical. And this here I show the orientation of the thousand passive vectors are distributed isotropically on a unit sphere. And in simulation, we start with many passive vectors distributed at the same point with random orientations. This is an example of the time series of 1,000 passive vectors. Initially, they distribute isotropically. After one period, they partially are aligned, and after two time period, they align on a sphere, on a plane that we call this is planar type. And in the third 3 times period, after 4 time period, in this case, it aligned on line. We see only 2 points, and we call this linear type, and so on. And we did this same calculation for many points. So we distribute 5,320 sets of passive vectors uniformly in space and at the initial instant, and each set composed of 1,000 passive vectors like this, and with random orientation. And we calculate standard deviation of the direction vector. This is unit vector, and averaged over 5,000 set. And this is the result. This is time, and this is standard deviation. It decreases very quickly. Means the passive vector aligned very quickly. this is the population ratio, evolution of population ratio. And this line shows the population, relative population set, which has the value of the standard deviation less than 0.1. Of course, initially it's 0, but increases very quickly after 3 times the period. More than 90% of the set has smaller standard deviation than 0.1. And if we decrease the threshold, we have similar behavior. And so the passive vector which start at same position with random orientation will be aligned in a few period of UPF. So we have this question. Can we expect the direction field of passive vector in UPF is uniquely defined irrespective of the initial condition? So we construct the direction field numerically. And we divide again the computation box into many cubes. And we distribute single passive vector in each box, in a small box, and track numerically the motion of the passive vector a long time. And we store the data, position, direction of each vector falling in the individual cubes every time phase. Actually, we store in 10 time phase and calculate the direction distribution of vectors in each cube. And now we classify the type of directional distribution. This is linear, this is planar, this is scattered. And we introduce this directional matrix, so we can calculate numerically this directional matrix. This is unit vector. And because this is the symmetric tensor, we have 3 real eigenvalues. We calculate this, and we calculate also eigen vector numerically. And to define the type of directional distribution, we introduce the model distribution like by this. Here we have 2 parameters, alpha and beta, in this range. And if we distribute vectors uniformly in this region, then we find the eigenvalue of the direction matrix. Lambda is related to this alpha and beta. So we can calculate numerically from numerical data lambda. Then with this relation, we can calculate alpha and beta. And this is the I show the result. This is the result at time 0.5 t, and the horizontal axis is the alpha and vertical axis beta. And note that horizontal axis is expanded 3 times. So this is 30 degrees. And this means, this line means more 90% of the small cube has included in this area. So that means in most cube, the vortices deviation is very small. So the alpha is less than 20 degrees. So that means the almost all places the passive vectors aligned in a plane. Okay, and we tentatively classify the linear, planar, and scattered, like this. So linear case, if beta is less than 30 degrees, we call that linear, and if this condition is satisfied, we call planar, and the others scattered. And this is the result, the relative population of linear region, planar region, scatter region with this size of box. Of course, this depends on the size of cube. So we checked the cube size dependence. We make the size halved. Then we find the scatter region is smaller, and if make further smaller, the scatter region disappear. So we have only linear region and the planar region. Now we examine where the linear and the planar types located in the flow field, and we compare the type of directional distribution and the flow state flow. So if we compare these two, the linear region exists in a vortex center, and the planar region is the periphery of the vortex center. And this is the cross stream plane, and this is the ejection region. This flow comes here. Ejection region, we find the linear region, linear type, and this sweep region, we see the planar type. So, so in this study, we found the passive vectors which start same position with different orientation will be aligned in a few periods, and we can define the directional field of passive vectors. And also we found the most of small cubes. In most of small cubes, passive vector align either in a plane or in a line. And so a linear type is found in the center of stream-wide vortices, and also the ejection region, and planar type is periphery. And I hope this the dispersion of orientation passive vectors may be used to quantify turbulence mix, some of the property of turbulence mixing. Thank you very much.
If you could do these calculations not for UPF but for the turbulent case, you would expect qualitatively different dispersion of these passive vectors, would you not?
You think so?
I'm asking you.
Yeah, I hope that we expect the similar.
For instance, this alignment into planar and linear things would not occur probably the same way.
The merit of this using the UPF is we can get a lot of data. But in turbulence, you need you must distribute many particles.
Right. We hear you focused on orientation. I was just wondering about magnitude. Do you see typical growth rates, or that is there Lagrangian chaos in these periodic solutions?
I think the alignment related with stretching. So,
of course, and you have the multiplicative ergodic theorem for chaotic systems. It would imply alignment at long times with the principal eigenvector. if it's chaotic, but I'm just wondering, is there Lagrangian chaos in these periodic solutions? Or
periodic solution, I think, was also chaos and has positive Lyapunov number, and I
what
think
is the
that's
Lyapunov exponents?
Lyapunov, yes, yes, the same. I think the same behavior as.
But why would a planar orientation survive if everything lines up with the principle?
Well, it could be.
Maybe it's a non-chaotic region?
I think that come from the complicated
Okay.
fractal or some. In a chaotic region, we have regular region, and that's very complicated.